Well, I'm very pleased to introduce Kirsten Siebach to you. I've known her for about 6 years. We joined the Curiosity mission, the Mars Science Lab mission, about the same time, and it's been a great pleasure. She's one of the mainstays of the science on the mission. Kirsten's path there is a bit unusual. She became a Martian basically in her sophomore year in college, when her advisor, Ray Arvidsson, dragged her into working with the Phoenix mission, which you may remember was a lander on Mars. It was up in the North Polar regions, dug down, scraped out to uncover ice there. Kirsten was involved in that as an undergraduate, and she tells me managed to fool most of the people around that she was actually a grad student at that time, until she was unable to rent a car. So anyway, so she finally got her bachelor's degree from Washington University, St. Louis. And I'm not sure whether it was a Bachelor of Arts or Sciences. It shows up both on there. I don't suppose it matters all that much anymore, but it comes out both ways. Anyway, from there, she went to Caltech, continued her work on Mars, working with Dr. John Grotzinger, who was the first project scientist for the Curiosity mission that we'll be hearing about here. And she worked there till 2016 and got her doctorate on the sedimentology of Mars and in this area. And in between those times, she was also working in the operations of the mission, the science operations, planning what we were going to do each day and what order events were going to happen. And so that was how I met her first. From Caltech, she went to SUNY Stony Brook for a couple years postdoc with one of the premier geochemists in the country. And then in 2017 was hired by Rice, and she's now working at Rice as assistant professor there. And her website says that she's very interested in education, which is not really a surprise, but also that she enjoys social dancing. So perhaps she can do a few steps for us. I don't know. In any case, thank you very much. Let's welcome Kirsten Siebach.
All right, thanks for that introduction, Alan. I am excited to be here tonight to tell you about Mars, how our view has changed over the past about 50 years since the Lunar and Planetary Institute was founded, and how curiosity has really contributed to our understanding of that and where we are right now in our understanding of Mars today. And so I wanted to start by going back, looking back at what we understood about 50 years ago and what we understood before that. I had to do some research there because I wasn't around. Starting before that, though, if we actually back out, one of the first geologic maps of Mars, one of the first geomorphic maps that we have of Mars was made by an Italian astronomer in the 1870s named Schiaparelli. And he looked through a telescope and mapped what he saw on Mars, and it was crisscrossed with these long linear features, which he called canali, or channels in Italian. When this got out, we're not actually sure what he was looking at. It could be scratches on his telescope or his eyelashes. It was a very creative interpretation of the surface of Mars. But what happened was the English at that time were in their canal digging phase. They were digging canals in order to transport goods more effectively from city to city. And so when they saw this map of Mars and heard Canali, they interpreted these as canals and said, oh, this must be an extremely advanced civilization who has learned to transport goods across the whole planet. And so that kind of started off this idea of these green men and Martians and how advanced this other civilization must be and how we need to get to know them better and understand it better. And so we continued to watch Mars through our telescopes in the decades following. And these are some of the best images we had before the space age. And so these were some of the images taken from telescopes of Mars. And we had started to get the feeling that those canals were a little fishy, but we continued monitoring. And you'll see these pictures are this is a compilation of some of those telescope images, and they're taken every 2 years. One Mars year is about every 2 Earth years. And so these would be of kind of the same side of Mars. And you see that dark and light patches are actually shifting around. And one of the features we've since learned about is that Mars frequently has global dust storms in which a lot of dust is lifted up from the surface, launched into the stratosphere. We're actually at the tail end of one right now. It happens about on a decadal time scale. But so that's what they were observing through their telescopes. As we looked at Mars over the decades, we saw periodically these global dust storms. And so these dark features would disappear and reappear. But that was interpreted as, this civilization, these areas with life, vast deserts, kind of a lot of change going on the surface. We were very enthusiastic about this possibility of civilizations and life on Mars when we decided to do when we got our first successful flyby mission in 1964. And that was the Mariner 4 mission. And these were a couple of the images that Mariner 4 sent back. Mariner 4 happened to imaged about 1% of Mars' surface, and the area it went over happens to be one of the oldest surfaces on Mars. And so what we saw were a lot of craters of varying sizes, but a lot of very large craters. And the kind of accumulation of very large craters only happens on surfaces that are about more than 3-4 billion years old. And so when we saw this, we realized that maybe Mars was more moon-like than Earth-like. I loved this from the NASA press release at the time. It said, man's first close-up look at Mars revealed the scientifically startling fact that at least part of its surface is covered with large craters. So this was about where we stood 50 years ago. And we have learned so much since then. But at that time, it was one of our first big realizations, maybe Mars doesn't have these advanced civilizations. It's looking a lot more like the moon. We realized with this mission that it had a very thin atmosphere, and based on these craters, that it had a very thin atmosphere and not much surface change for billions of years. And so this called into a lot of question whether or not we should continue going to Mars. Luckily, we did a few more flybys. Interestingly, the first 3 flyby missions actually only imaged craters on the surface. But a few years later, we got the Mariner 9 mission, which finally captured one of the channels. So Mars may not be crisscrossed with these large canals, but instead it does have a number of channels and features that tell us that there used to be water flowing across the surface. And so this was one of the first captures of one of those images, again on a flyby mission that just took a slightly more fortuitous path around and managed to catch at least one of these channels. And so we got excited. Okay, there are channels. There used to be water. There's something more interesting than the moon. But no offense. There's something more interesting in terms of surface activity. It's a little bit more Earth-like, or it was at some point. In the later 1970s, we finally got to send 2 landers to the surface of Mars and 2 orbiters, and those were the Viking missions, Viking 1 and 2. With those, we managed to get color coverage of the whole planet, and we could see that there were, in fact, a number of scales at which there are ancient channels preserved on the surface. And so we realized at this point, okay, there were definitely water flow features. There were some kind of large floods that caused these channels that will run hundreds and hundreds of kilometers across the surface, thousands of kilometers even in a couple of cases. There are smaller scale networks that show rivers flowing across the surface, potentially fed by glaciers or maybe rain. And so we were a little more excited. There's definitely water that flowed across the surface. At the same time, we realized that there probably isn't plate tectonics. There isn't the same level of activity as we've had on Earth, and there isn't as much. The plate tectonics gives us the advantage of being able to see units of rock. And so this is something where we can see where the water flowed, but it may be tricky to see what was carried in that water. We decided to investigate with landed missions anyway. So we sent a number of landed missions in the well, actually, there was a long gap because we were afraid that we wouldn't be able to find anything. But in the 1997, we sent Pathfinder, and then 2004 kicked up Mars exploration with the 2 Mars exploration rovers, twin rovers, Spirit and Opportunity. And at this point, we'd scanned the planet. We said, all right, what kind of places would we like to land where we might learn about this ancient water? We think the ancient water is key to the possibility of ancient life. And so with Spirit, we found one of the long channels that ended in a crater. And this long channel goes into this crater and actually comes out the other side. And we said, okay, so this crater will give us the lake beds that were deposited by that water. And so we picked that for the Spirit rover. And for the Opportunity rover, we had gotten some chemical data across the surface. And one area on the planet lit up. So you can sort of see there's a lot of green and blue. And there's one area that's bright red right there. And that's hematite. It's an iron oxide mineral that forms in water. And so Opportunity went for that site. So we sent one to a geomorphic site and one to a chemical site. And 2008, we also sent a lander up to the North Pole where we knew there was kind of frozen water ice at the surface. We didn't go all the way up here because it wouldn't have lasted for more than a few weeks. We went down a little bit further from the pole, but we were still able to dig and see pure water ice. And so in some ways, we were successful in our follow the water strategy. Spirit, unfortunately, after going to this nice flat lake basin, found only volcanic rocks. It turned out some of those volcanic rocks had interacted with water, and so we had a little bit of evidence for there being water maybe in the subsurface where these volcanoes were erupting or where the magma was coming up, but actually mostly volcanic. Opportunity was the one that found sedimentary rocks. And so this is the Burns Cliff. It was these were the first sedimentary rocks that we got to see from the surface of Mars. They were exposed in the wall of an impact crater. And so Opportunity is sitting inside of an impact crater and looking at what's been exposed on the wall. And these are sediments that were probably deposited in dry or just barely wet kind of sand dunes, but cemented by groundwater. So we were excited. We knew, okay, there are sedimentary rocks on Mars, and in some cases they are exposed. Maybe we just need to look in craters where impactors have done the digging for us. It's much easier to go somewhere that's already been dug out than somewhere where you have to dig. And so we can find places where water cemented the rock. Now, we looked at the chemistry of this, and it turns out the water that cemented this rock was very acidic. If you have a lot of sulfites, a lot of volcanic gases, a lot of volcanic emissions that interact with water, you can end up with very acidic fluids. So it's something like battery acid, which caused most Mars researchers to go look at places on Earth with very acidic environments. And we found that indeed life can still live in these very acidic environments. And we researched that kind of life, that kind of extreme life, and what we might be looking for on Mars. So we've kind of changed our paradigm to where we're looking for extremophile life that might be surviving in these kind of acidic groundwater environments. And in that point, we kind of transitioned our theme from follow the water, said, okay, we found some evidence for water at all of those sites. We found some evidence for water interacting with volcanoes, some evidence for groundwater, some frozen water on Mars today. Let's take the next step and explore habitability. So what do we mean by habitability? We define habitability as being, or a habitable location, as being a place that has the raw materials for life, or basically carbon, phosphorus, sulfur, oxygen, nitrogen. It has some source of energy. This could be the sun, but it could also be chemical forms of energy, like power batteries, different oxidation states of minerals or of elements like iron or sulfur. Generally favorable conditions. This can be poorly defined, but battery acid isn't usually considered a favorable condition. But we're looking, there could be ways to bend it, but we're looking. And definitely the presence of water. Now, beyond that, if you actually want life to kind of inhabit the location or for life to maybe potentially start there, you do need those conditions to last for a long time. We don't know exactly how long it takes life to start. We don't know how long it took life to start on Earth. But we're looking for kind of these 5 ingredients: the raw materials, the energy, the water, favorable conditions, and time. Beyond that, we have a couple requirements that are just based on trying to find these rocks, right? And one of them is that the rocks are preserved, and hopefully that the materials inside them are preserved. If you ever had little microbes in a rock, you want to be able to find where they were. You're going to need a place where microbes have been preserved, where there hasn't been, we'll just keep going back to battery acid, but battery acid flushing through the rock afterwards either, right? You need a place that had that water, but then was preserved in a way that maintained, that allows you to see the conditions that were there in the past. And you need the rocks to be exposed. This is an example where they're exposed in a canyon, right? If water's flowing through, it can erode the sides and actually show you the layers of rock. While that is a good feature, and we could also see layers of rock like that on Mars, we can't typically land a mission at the base of a canyon because we're sending signals to satellites orbiting in space to send the signal back to Earth. And so if you're at the bottom of a canyon, you have a very restricted skyline. And so while that's a source of layered rocks, it may not be the best one for a landed mission. And so we have to look around a lot actually to find a place where the rocks we're interested in would be exposed at the surface, especially because Mars lacks plate tectonics. So without plate tectonics, you don't have continents shifting around and actually elevating layered rocks to the surface. So this was actually a greater challenge than we thought it would be. And in the mid-2000s, we started to find evidence for situations that happen on Mars that don't typically happen on Earth that help us with this. So I'll show you an example. These are a crater system. These are Holden and Eberswalde craters. There's a few craters. This one is Eberswalde. It's an older crater. And then this one is Holden, which is a big impact crater that actually splashed, we call it ejecta, into the Eberswalde basin. That part, after these craters were established, there were some of those canyons again, some of those rivers that actually flooded this system, caused a lake in this crater that then breached one of the walls, looped around over here, came into this crater, which also had a lake in it, and then it breached and actually continued out. I'm going to zoom in on that white box. What we're seeing here are when there were actually rivers coming in, those rivers deposited sediment right where the river entered the lake. So the rivers are moving fast, they can carry a lot of grains, they can carry rocks, and when they hit the lake, it slows down, the momentum of the water is lost, the rocks all fall to the ground. That's called a delta, when it's underwater where the river enters the lake. And what we saw when we looked here is that we can see actually the rivers where they entered into the lake and dropped all their sediment, and they're standing tall now. We call this an inverted deposit. Normally, if you look at a landscape, the river is a depression. And in this case, the rivers are elevated. And the reason for that is because the only reason this is showing up is because on Mars, the dominant force for the last 3 billion years has been wind. And as wind goes through, wind can move fine particles, but it can't move coarse ones as easily. And so the wind has actually come through this crater repeatedly. It's blown away the fine particles that made up the river banks and the sides, or the lake, and left just the channels that filled it up, the deltas, the river channels that were actually coming into the lake here. And so this is an example of some place where we could go on Mars and we could climb up through these different levels and see how the rivers change through time. We could see the rocks that came down in these rivers, in these floods, and see what happened in the early floods, later floods, as we kind of climb up through the layers. So we have a mechanism on Mars for exposing ancient rocks, and that was key. And we looked all over Mars for any of these places where we could see the layers. These things on the left, these are called stratigraphic columns. And what we did was everywhere we could see the layers, we flew over with another mission and we looked for the mineralogy of the layers. And when we found minerals that we knew were associated with water, clay minerals are an example. So clay minerals form in water. Those are all color-coded in green. Salts form when water evaporates. Those are color-coded in yellow. And then iron oxide is really just blowing around in the wind and has been for about 3 billion years on Mars. And that's color-coded in brown. When we looked at every place where we could see layered rocks, we tried to see kind of where they were, if we could guess about how old they were, and what they were made of. And the oldest ones tended to have more clay. We think Mars had more water early on. Then the middle ones kind of have more salt, and the youngest ones are just dry. If you look at all these columns, there's actually only one that captures all 3 of those units. And this is Gale Crater. And that's essentially how we chose that for our landing site. Said, all right, we want to be able to understand what happened through those different time periods. We want to be able to climb through layers of rock deposited at key times in Mars history and see how things changed. This is Gale Crater. These are the layers. This is an interesting case because this crater is about 110 miles across. And actually, we think that the entire crater probably filled up with different sediments through time. And then the wind came, and the wind actually kind of dug down into the ground and dug a moat around the crater. And so you're left with this feature in the middle, basically a mountain in the middle of the crater that's more than 3 miles high, and the wind blowing sediment around it in a moat. And that's cleared up the layers that were originally deposited in the crater. I've got a zoomed in picture here. So we picked this as our landing site. We needed a flat spot to land. And then we drove over here where these layers are all exposed on the side of this mountain. We call it Mount Sharp. As you can see, this is actually a process that's still happening on Mars today. The wind is still blowing sand. This dark material is dark sand blowing today. The wind is coming from this direction, and it's actually blowing around this mountain in the middle of the crater, accumulating in the back of the crater, and actually some of it's sliding out right out of the crater today. And so this is an actually eroding system, which is great for us because there's dust all over Mars. And so places where wind is moving things away and blowing away that sand helps clear away the dust and helps us see those layers as clearly as possible. It's probably why we could see all of those different minerals in those layers to begin with, and why this was chosen as a key site to understand what Mars was like at those times and whether or not we could chase that habitable environment. When we first landed, this was one of the first images, and I just love showing it. It was just so exciting after years of studying, Gale Crater from black and white imagery above to see it like we would see it with our own eyes. So we actually adjust this image, we white balance it. The sky isn't really blue on Mars, but if we balance it to have a white sky, then the rocks are the same color as we would see if those same rocks were here on Earth. And so we look at the image, we get to see, like a geologist, like someone out hiking, what it would look like to be next to Mount Sharp. And even from this distance, we could see those key layers. We could see where the sand was blowing around at the base. We can see this kind of hollowed out layer where the clays are. We can see very clear layering for the salts, the sulfate salts. And then there's kind of an unconformity above which we mostly have dry dust. So we're most interested in capturing kind of these transitions in the base of the crater and asking about, is this a place where life could have lived? Now we have about 400 or 500 scientists and engineers on the team that operate the rover, as Alan was mentioning before. This is an overhead image of our landing site. This is where we blew away the dust as we actually lowered the rover down to the surface. And this is the direction towards those beautiful layers that we got to image from the ground. And when you have 400 scientists driving one car and there are no roads, there's a lot of discussion about which direction we want to go in. But this one, it was very clear which direction we wanted to go in. And this was probably the only time we had a unanimous decision as to which way to go. The other way. I think it really was the only time we had a unanimous decision. But you can actually, this is an actual overhead image, and you can actually see the rover over here. This was taken back in 2012, but you can see the rover, and you can see its tracks as it did this little jog right over here. Now, the reason that we decided to go in that direction was because there were a couple of different units we could see on the surface just by color. This light tone unit was one of interest because it is the lowest elevation unit in the crater. And if you're telling the story of sedimentary rocks, if you're telling the story of what happened layer by layer, you want to start with the oldest layer and move up to younger and younger layers. And so we wanted to start the story at the beginning, or as much at the beginning as we could. And also, water flows downhill. And so we just wanted to see that lowest point in the crater before we went over to Mount Sharp. And as you can see, it was about 500 meters away. We had about 8 kilometers to go to Mount Sharp. And so we jogged over here to see this. And as we started, some of the first rocks that we saw were these conglomerates. These were actually cleared off by the blast zone as we were dropping the rover onto the surface. And these conglomerates is a geology word for these rocks made of debris of other rocks. And the key point is that debris, those pebbles, are rounded. So if you look closely, like this pebble has rounded edges, or this one is very round. And so those rounded edges come from water, right? Come from being transported in water and banged up against each other. And so pebbles of this size carried in a stream that actually get banged up against each other, we can tell from the size of the pebbles that get carried by the stream about how deep the stream is. And so this river was actually, was knee to waist deep, flowing across the surface of Mars. This is awesome to find these rocks. This was the first time we could see, very clear evidence from the ground that we had water flowing across the surface. And so we're heading in the right direction. We're doing this right. We landed in the right place. And so we drove over to that low point. And this is kind of what that looked like. We stepped down off of the coarser grained conglomerate sandstones that were being carried by a river and onto that light, flat unit, which I've got a keyword giving it away here, but it's called the sheepbed mudstone. And we said, okay, this is a very flat, very fine-grained rock. Those kind of form in very calm, watery environments. And so this was the place we decided we'll take out the Curiosity's robotic arm and collect a sample to get a little more detail on what happened here. When we drilled into the rock to collect our sample, one of the first things that we saw, and actually the thing that we were really excited by, was that the rock was not red. Everything on Mars really is red. We call it the red planet for a reason. There's this red iron oxide dust blowing across the surface all the time. And that kind of indicates that the whole thing is radiated. There's a lot of radiation from space. There's no magnetic field to protect Mars from that radiation. And that kind of oxidizing radiation is pretty dangerous if you had, we would get pretty badly sunburned. And DNA or microbes or anything that might have been in the ancient rocks would also be degraded by that kind of radiation. Also, the rocks are typically oxidized by that kind of radiation and any kind of water interaction. And so finding rocks that were gray means that not all of the iron is oxidized. There are places where the rock has been protected. And like I said, this crater is actually still blowing away. And we think that part of this is that some of this rock could have only been exposed for only in geology terms, hundreds of thousands of years, right? And so this could be places where there have been rocks that were protected for the majority of the 3 or 4 billion years since they were deposited that are now exposed. And we can find places like this. This is just optimal. If we can find places like this where we don't have to dig that deep to find places that have been protected and might preserve evidence of what was happening in these ancient lakes. Because this did tell us that we had an ancient lake. We had a couple, Curiosity is called the Mars Science Laboratory because it has a number of laboratory instruments. And 2 of the key ones, when we drill into the rock, we're able to do 2 key analyses that tell us about what the rock is like. One of those is reflecting X-rays off of the powdered sample. And when we reflect the X-rays off, we can detect what minerals are there. The X-rays kind of bounce off mineral boundaries. This was an example of reflecting X-rays off of a blowing sand on Mars that's just blowing in the wind. And this is reflecting X-rays off of this sample. And what you see is this bright patch right here, and those are called phyllosilicate clays. It's a certain mineral that definitely forms in water. We can characterize it well using this instrument, and so we know that this was actually neutral water. This was a freshwater lake sitting on the surface of Mars. It wasn't too salty. It wasn't battery acid. It wasn't some crazy pH. It was pretty much a typical lake. The other trick we have is that we can heat up the sample. So this plot goes over to 1500 degrees Fahrenheit. And as we heat up the sample, the thing about those clay minerals is that they're formed with layers. And when they form in the base of a lake, those layers will actually trap some of the lake water in between the layers. And when you heat up the sample to 1500 degrees, it pulls apart the layers and releases what's been trapped inside. We call those the volatiles. And that tells us basically what the chemistry of the lake water was. This is preserved kind of evidence of the lake in those minerals themselves. And so when we broke it apart, we saw that it was water. It was water. It was a place where there was energy for life. There were multiple states of iron. There were multiple states of sulfur. And so this is pretty ideal. This actually fits all of our requirements. This is a habitable environment. So we were absolutely thrilled that we drove in the wrong direction from the beginning, because this mudstone, this revolutionized our picture of Mars. Before that, we had some sedimentary rocks on the surface, but to be on the ground and find a lake, it was probably about 3.5 billion years old, that would have been on Mars and been a place where Earth life would have thrived. It would have been fine in this lake. And so we didn't find evidence for life here, but we definitely had environments on that planet that would have been habitable for Earth-like life. As soon as we did that, we said, okay, well, what's the next part of the story? Let's drive back towards the mountain. This is one of my favorite pictures as we're driving. Just as you can see those layers, you can see that dark sand blowing around, and you can just see the layers as we're approaching them. We kind of book it towards the mound, and what we realized as we booked it towards the mound was that we were seeing a lot of layers that were kind of rocks that were dipping down in the same direction. We say they're dipping down like this. We're following rivers as they go downstream, essentially. And so we actually climbed up through a lot of different rocks, and they're all going downstream. So we could see that we were looking at river deposits, and remember that delta that I showed you in the Eberswalde crater. Well, these ones aren't preserved in quite the same way, but these are all rocks that are deposited by rivers as they're entering into a lake. And so we saw this for about 2 years before we finally got right back here to where we crossed over into the lake deposits. These are some of the lake deposits. So lake deposits are characterized by being really fine-grained and these really long, flat layers. They'll continue for meters in either direction. Because if you picture a lake, it's just the little tiny bits of sediment that sink to the bottom of the lake. And you can have seasonal changes and different things that cause there to be these layers in the bottom. And so these may be annual layers, actually. We're not sure. They could be seasonal. They could be event layers, like every time you had a hurricane, not exactly a hurricane, but different floods or different years produce these layers. And we started climbing through these layers. We got really excited. Each layer takes at least a year to actually settle down. These are some of the thicker layers. They're up to 1 centimeter thick, but the majority of them are just millimeters thick. We start climbing through that, and we get to see the history of that lake through time. So step one, we definitely had a big lake on Mars. It was about 3.5 billion years ago, sometime in between 3.2 and 3.6, probably about 3.5 billion years ago. Step two is that as we climb through it, we get to see how that lake changed with time. And we kept climbing through it. We were climbing and climbing and climbing, and we are just climbing through this lake sediment. So actually, we've been climbing through it now for almost 4 years. And we were really excited by it first. It's getting a little boring, but but the exciting thing is that this lake lasted for a very long time. So at the base, when we first started driving, this is kind of our traverse path. There's a little rover going up, but this is elevation and distance. And you see it's gotten steeper as we've gotten to the cliff. We actually climbed all the way up to here, which is about where we started detecting some of the strongest signatures of clay from orbit. But then we actually jogged back down. What happened was that we got to about right here, and our drill broke. And so we continued for a while with a broken drill, just getting kind of chemistry measurements. But when we finally got the drill back online due to some brilliant MacGyvering by the JPL engineers, we kind of jogged back down to actually get some drill samples so that we would really understand what we were driving through. And so that's where we are right now. We're getting the second or third drill sample since we've gotten the drill back on track. But this distance is actually quite significant to have millimeter thick layers deposited by this lake through time. And so if we kind of calculate it, we just do a back of the envelope calculation. We use our big rivers on Earth or big lakes as examples. We say if we've got 300 or more meters of laminated mudstone, that's probably about 3 million years of standing water on Mars. Just finding the lake really revolutionized our picture of Mars, but now understanding that that lake lasted for such a long time is really pushing us to reevaluate our understanding of how the atmosphere on Mars worked 3.5 billion years ago. We kind of thought that at that point the atmosphere had mostly been lost, and it was unlikely that liquid water would stay on the surface for very long periods of time. Finding a lake that lasted for 3 million years really pushes us to reevaluate that. And so we're really trying now to understand what the climate could have been like, because we don't think the atmosphere was very thick and the sun was less bright, but somehow we certainly had conditions where the surface stayed warm enough for that water to be liquid. We're not even seeing major indicators of ice. You don't always see indicators of ice, and so it could freeze or could have an ice layer at the surface, but we haven't seen any evidence of it. And so we're kind of pushed to believe that Mars had surface water sitting there for much longer periods of time than we previously anticipated. We have drilled in it a number of times. Oh, this is one of our selfies. We tend to take selfies when we're drilling. We love our little selfies because this actually, it actually takes us a full day to take a selfie on Mars. This is a one-day activity. It takes about 80 or 100 images. We've got one little camera on the end of the arm, but it's got a very small field of view. And so we have to hold the arm out and then take like long mosaics kind of in all different directions and then cut the arm out of all the pictures to get these selfies. This is one of our examples, and we tend to do them when we're stopped to drill because we'll stop in the same place for a while. And so this is one of the drill holes right there in the surface. You can see it's still gray, still telling us that that lake had kind of different chemistry than Mars has today. And here's actually, so we've gotten a number of samples from that lake, and we're really still investigating this because we're really trying to understand the details of how the climate changed through time. Those very first samples that I told you about in that first kind of lake that was actually separated from this other one by a ways, right up here, were distinct, so the other lake looks like it was actually in a slightly warmer climate. And we're still trying to kind of understand the intricacies of how it changed through time. We know there were a couple episodes where it seems to have gotten sediment from a different location, and a couple episodes where you had different, we call them redox conditions, but more oxidized iron, less oxidized iron, kind of shifts in between these things. And that'll tell us as we keep investigating it. And actually one of the other tricks is the exact way that the clay formed tells us about the climate. And that also tells us that there were periods where it was slightly warmer and slightly cooler, but actually continued to be a fairly habitable environment, a place where life could have lived, a freshwater lake, all the way through so far. And so we continue to drill. Like I said, we had climbed up and now we looped back to get a couple more drill samples. And that's where we are right now, kind of capturing that terrain that we had driven over originally before we continue up the mountain. One of the exciting, let me see, it's this drill hole right here was near the base of this longer stretch of mudstone. And one of the exciting findings that just came out this year was that we did find some organics in that material. Now, organics are just carbon-based molecules, but that's what we're made of. So we get excited when we find carbon-based molecules. They can also come from space. So they can be delivered by meteorites. They do form naturally in space. If you go out by Jupiter, there are whole planets that are covered in these. But to find them on Mars, in this 3.5 billion-year-old mudstone, is particularly exciting because it fits one of those criteria that we need to find habitable environments. So whether these organic molecules came from space or came from some form of early life, they were preserved in the mudstone, and they still exist. And so if we were able to bring this sample back, we'd be able to characterize them in greater detail and figure out if they did come from life, some kind of biologic process, versus more like, well, our default is to assume that they're coming from meteorites from space. But this kind of cinched the last step, right? If you're going to look for organic material, if you're going to look for life on Mars, one of the key things is that it needs to have survived that 3.5 billion years. And so the fact that in one of our 10, 12 drill samples that Curiosity's taken, driving across the surface, that's not that many samples. Now we did pick a good place, but we don't have that many samples. And the fact that we already were able to find preserved organic molecules is actually a really good sign for being able to answer that question, for seeking to answer that question, was there ever life on Mars? If we could bring a sample like this back, we'd be able to really characterize the organic molecules in there. The only reason we can't perfectly right now, we think that it's kind of a large organic molecule like kerogen. And so when we heat it up in our little oven to 1500 degrees, we get kind of broken off pieces that are reacting with other components in the rock. And so because we're heating the whole rock up, it gets the chance to react and combust and create these little broken pieces. So what we're seeing are the broken pieces that are evidence of a larger organic molecule. Now, this is exactly the kind of molecule we would expect to be delivered from meteorites. And so we're still on that track. But being able to preserve organics was really an exciting discovery. So Mars really does fit all of these kind of characteristics of a planet that would have been habitable. And in fact, we kind of think 4 billion years ago, Mars and Earth might have actually looked very similar. They might have both had liquid water sitting in pools on the surface. They might have both had organic input from space that might have been sitting in the lakes. We don't know if Earth had plate tectonics at that point yet. And so, interestingly, Mars actually preserves this story of what was happening 4 billion years ago even better than Earth does. On Earth, we've got water flushing through everything. We've got plate tectonics mixing it up. If you look at a timeline of the planets, they both formed 4.5 billion years ago. But Mars, most of Mars' surface preserves that time before 3 billion years ago. For the last 3 billion years, it's been mostly dry and windy. So it's actually got a very good record that's accessible for what was happening between 4 and 3 billion years ago. Now on Earth, most of Earth's surface is definitely from the last billion years. We are able to dig deeper. We've got better tools because we're here. But we do think that our evidence for when life started is right in that time period of about 3 to 4 billion years ago, that we've only got a few rocks preserved. Most of them have been kind of flushed through with water, altered by heat, buried, brought back up to the surface. And so interestingly, one of the things that's come around is that Mars can teach us about Earth. Mars can teach us about what early Earth might have been like. Mars actually offers us a chance to see what happens maybe in an environment without life. Maybe even if Mars doesn't have any life at all, it shows us a contrast to what we see on Earth, where life is everywhere and even affects the way that rivers flow and glaciers move, and everything that happens on Earth is affected by that. We've never had a control experiment in geology, excuse me. And so Mars is actually offering us a new perspective on our own planet. And that's one of the kind of revolutions, I think, of the way we think about Mars. I wanted to tell you a couple of quick stories about Mars today, and then just tell you what's coming up next. So Mars today is also more active than we thought. As we've been driving around with these rover missions, we've discovered a little more activity than we anticipated. And just a couple examples of that. This is the wind moving sand from one day to the next, January 23rd and January 24th last year. So the wind is very actively moving sand. There is wind moving. It is not as powerful as the Martian would make it out to be. It would not knock over Matt Damon. But it is moving, and it moves sand. It's just, you've got about less than 1% of the atmospheric pressure of Earth to actually blow. One surprising finding is that methane, this is a plot of methane versus seasons, and every now and then we get spikes of methane. It's a gas in the atmosphere that on Earth is mostly associated with biology, and those kind of periodic releases of this gas were unexpected and are still unexplained. There can be reactions with rocks and hot fluids, maybe very deep in Mars, that could produce this kind of gas and allow it and then movements of rocks could allow it to escape on a seasonal basis. But this was really something that has come out of curiosity in the last year, and we are still trying to understand how that could be happening, and it prompts a lot of discussion about whether or not, biology, whether or not there could be pockets on Mars where extant life could still exist. It's really pushing it, but it's exciting. One of the other ones that was recently found was up near the North Pole. We had a bright reflection from one of our radar instruments that led researchers to interpret that there could be a subsurface liquid water about 1.5 kilometers below the surface, below a glacier. And so that is currently being disputed, currently being discussed, but it would be pretty exciting, even if it's a really salty sludge, right? There's still that kind of possibility. Life on Earth always exists. Life on Earth exists everywhere. It exists in every extreme environment. This would be a very salty, very cold environment. Again, not really favorable conditions, but it's exciting nevertheless to think that Mars today could have liquid water and maybe reevaluate our view that those last 3 billion years have been quite so boring. We also see these dark streaks. This is over the course of a Mars year, as those streaks actually come down the side of a crater. And those expanding streaks are oft discussed as to whether or not liquid water is responsible. Okay, so what's coming next? We have the InSight mission is arriving on Mars November 26th of this year. It is already en route. We are hoping that this global dust storm episode has kind of calmed down by the time it lands. And that one will stay in one place. It will take some pictures of one spot on Mars, but it will stay in one place. It doesn't have wheels. And it will deploy a seismometer and try to understand a little bit better what's going on inside of Mars. How much heat is escaping, and is there any activity in terms of a core or seismicity? Mars quakes. It will look for Mars quakes. And the next big one is arriving on Mars in 2021. Right now we call it the 2020 rover because it will launch in 2020, and we have not yet had our competition for school children to name it. But that rover will be very exciting because it's modeled after Curiosity. It looks just like Curiosity, but its main job will be to acquire rock samples. And those rock samples will be about the size of your pinky. It will acquire up to 30 of them and leave them sprinkled across the surface. The idea will be that you then send another rover that comes and it picks up all of the little samples that we've acquired. So you now have a box of pinky-sized rock samples. You take the box, you launch it into space, and then you have another mission that comes from Earth and grabs the box out of space, brings it back to Earth. That will take a while. But this is the first step in actually getting samples that we select and bringing them back to Earth. The only samples we have on Earth that we've been able to analyze from Mars have been meteorites that were actually knocked off of Mars by major impactors on Mars, launched into space, and happened to land on Earth. We have a couple of those. We have several of those. But it will be really nice to be able to investigate rocks that we have context for, that we know where they're coming from, and we can piece together the story, because the order of the layers of the rocks and where they're coming from makes a big difference in understanding the story of Mars. Those will be some of the most expensive, precious little rocks on Earth if we get them back, fingers crossed, in a few decades. I love always showing, this is a picture that actually just came down from Mars. So this is Curiosity's next steps as in tomorrow. So we're looking at the ground right here, right now, and looking at kind of rocks to zap with the laser. We, as a science team, we get to make decisions about what we want to zap, what we want to take pictures of, and then which direction we'll go from here to our next stop. And our next stop, again, is kind of picking up one of those drill sites to make sure that we understand that rock that we drove over before. Next steps over the next few months are that we are so close. This is actually the first part of the transition between the clays and the sulfates. So I motivated this earlier by telling you about how this was a spot where we could actually see major transitions on Mars from when there was water to when there was less water to when there doesn't appear to have been very much water at all. And this is the first one of those transitions. We should get here in the next several months, kind of thing, maybe in the next year. But this white patch is actually the transition from the area with the most clay to where we start to see a lot of those salts. And maybe our lake started to dry up. And we want to be able to understand that from the ground and see the record of climate change on another planet. This was a dramatic climate change on Mars that can tell us about, global scale climate changes and what's recorded in the record, where to land next. So thanks for listening, Curiosity. I love this picture. I just love the selfies because it really does make us relate. This is one of the other things that's been really powerful about having these missions on the surface of Mars, is that those of us driving the mission, but also everyone in the public, can feel like we have a friend on Mars, right? Mars is so close. It's so real. It's a place that we've seen pictures of that look just like Earth. And so really one of the revolutions in the last 50 years, right, has been that we get to experience other planets. Now we have virtual reality headsets. We actually walk around on Mars in our offices. But that we really get to experience Mars as another place, that we can compare it to Earth, that we can understand its geology, understand its history, understand the story that it tells us about the early solar system and even our own planet, and help us explore and be motivated to look beyond what we see right in front of us and think about the broader scale. And so it's been so much fun to work on. So thank you.
Okay, I really like the history of Mars exploration. That everything she just covered really well. Interesting thing, Carl Sagan said after Mariner 4, he said, I could image 1% of a portion of Earth's surface and it would look like no life existed on Earth. I like that. Okay, so take some time for some questions. Raise your hand. We'll bring you the mic.
On the previous picture, what is the elevation that we're looking at?
Well, so elevations on Mars are determined by we've established a sea level, which we started about 4,500 feet below, 4,500 meters below sea level on Mars, because we were deep in Gale Crater, which is actually about 4,500 meters deep. So sea level is about the top. We started at minus 4,500, and we have climbed up about 400, so we're at around minus 4,100. So this cliff is definitely taller than the rover, so we are hoping to be able to drive up. We were actually analyzing whether this was too steep. This is a quite steep cliff, so we've been trying to figure out if we'll be able to reach this part of the rock, or if we'll have to go kind of off to the left side where that light layer kind of reaches. So it doesn't give you a perfect scale, but it does tend to be hard to show scale in these pictures. A lot of things can appear smaller than small. That's why the virtual reality headsets are great, actually. You realize that you and 200 other people have been looking at something this size and arguing about it.
On one of the previous slides, you showed Curiosity's path with various spots that were named, and I saw names like Duluth and Cooperstown and things like that. How do you name those places? Are these your hometowns or something? Or
sometimes. So for each mission, we come up with some kind of a naming theme. For Curiosity, we divided the surface into what we call quads, which is actually how we divide the surface on Earth. So when we do geologic mapping on Earth, we divide the ground into sections we call quads that will be, I'm not sure of the dimensions exactly, but we grid the Earth, and then we map it out in grids and put the grids next to each other, and it's a convenient map scale. So on Mars, we identified kind of squares that we would work with, and within each square, we select a square that's on Earth, that's been geologically mapped. And we take all of the names from the geologic map on Earth, and we use those names for anything we see in that square on Mars. So we've gone through Yellowknife, Canada, Namibia, we've gone through Montana, California, Death Valley, the Kimberley in Australia, Pahrump, yep, we had some in Death Valley. So and right now we are in, not Finland, we're in somewhere, I'm blanking on where we are right now. Scotland, we're somewhere in Scotland right now. This is great, but it leads to some confusion when you work in an office with earth geologists working on the same region.
For a possible sample return mission, as a planetary geologist, assuming you could choose the site from which the samples would be extracted, what area of Mars would you choose?
So my opinion is biased because we've just been working through this. So we are in the process right now as a community of kind of contributing to that decision for the 2020 rover. And so we have narrowed it down as a community to three main sites that we're interested in. And so for me, my mind immediately goes to those sites and asking which of those sites I prefer. But I think overall, I would want some of the older terrains on Mars. I really would like an area that samples some of those oldest rocks that are 4.2 billion years old, because we really don't even have rocks like that on Earth. And so sampling them from Mars would be very valuable. And I work with sedimentary rocks. I work with the kind of rocks that are deposited through time in these layers. And I love the way that those tell us the story. And I think from those rocks, we can derive information about the rocks they came from. And so I would look for a place where a river had moved some of the oldest rocks on Mars into a nice basin, probably a crater similar to this, So a delta type environment where I'd be able to look at the rocks and see what are the grains that tell me about this whole area, and how are they transported. Plus, I know there was water in those kind of places.
Hi, two questions that are interrelated. How persistent would methane actually be in Mars's atmosphere if it were released from the rock? And then also, what would be the most dominant mechanism for methane being released from the rock? I mean, I assume there has to be some event for it to percolate up from the rock surface.
Yeah. So if that methane comes from water-rock interaction, which we always assume not biology when we're first thinking about it. So if we assume not biology, then it would be water interacting with basaltic rocks, and that would probably be somewhere deep within Mars where there's still enough heat to like have those reactions occur, or somewhere deep enough where there used to be enough heat and now that gas is trapped. The fact that it kind of releases in seasonal bursts, it could be that through the seasons there's a lot of temperature change on Mars between day and night, shadow and light. Day and night is 100 degrees. Shadow and light can be tens of degrees. And so that kind of causes thermal expansion and contraction. And so I think you've got some form of gas trapped at depth, and then some kind of thermal expansion and contraction through seasons allows it to periodically have a path to the surface, and you burst with this burst of methane. We can't actually explain, though, we haven't explained this very well. This is, we're figuring this out. We can't explain where that methane goes. So we actually think it should last in the atmosphere for a few hundred years if it was released, and we're not seeing that. The methane instead disappears. What we see, we keep calling it bursts of methane because we'll see a spike, and we're talking about a spike in terms of parts per billion. It's not a lot, but there are spikes that we can't explain. We don't know. And so if it's being released, it's also then being absorbed somewhere. And so there's two steps to the process that we are working on explaining. The fact that it's seasonal tells us that it is intrinsic to Mars. It's not something coming in from space, which is one of the explanations we had before. Oh, yeah.
Hi.
Hi.
3 quick questions. Talking about temperature. What is the warmest temperature that we know about on Mars? And secondly, I know you can't directly drive to those salt formations, but about how far from the rover is it as the crow might fly? And then thirdly, you had a collage a few charts back, and the lower right was like a crater wall or cliff, and it's a time-lapse photography of these streaks. And I'm wondering what's the latest thinking on those streaks. Initially thought maybe that's dampness, then maybe it's dry. So what is the latest thinking about that?
Yeah.
Thank you.
All right. So the warmest temperatures near the equator, in the bright sunshine, with the Spirit or Opportunity rover, we've measured temperatures that are certainly above freezing, above our version of freezing, which is 32 degrees Fahrenheit, right? So we're talking 40-ish. That is not above freezing on Mars. On Mars, the atmospheric pressure is so low that liquid water is never stable. So if the pressure is low enough, you go straight from solid to gas, and the liquid form is not stable. So that's the case on Mars. So although it would get up to above 32 degrees, it wouldn't become liquid. The latest thinking the latest thinking on these streaks is that, well, we've been going back and forth. You can't have liquid water on Mars. What you can do is if you have a salt that will actually grab some of the water, that can change the freezing point of water. We know that because, well, we're in Houston, but if you salt the sidewalks and it ices, right, you can prevent the ice from forming on the salt. You can kind of do the same trick where you actually depress the freezing point, alter the freezing point. And so if you have enough salt of certain varieties, you could have liquid water, or you could have wet salt. It's not going to be a lot more water than salt, right? It's just going to be that salt is wet. So one of the hypotheses was that these streaks are caused by wet salt. We have seen some of these salts on Mars. That the perchlorate salt is an example of one of these, and we have seen perchlorate salts sprinkled around on Mars And so this could be related to that. One of the latest studies, though, showed that the angle at which these streaks are forming is very consistent with dry granular flows, with just stuff that slides down the side of a sand dune, essentially. And so if you remove the dust, we know that if you remove the dust from anything on Mars, it looks a lot darker. And so these could just be sand slides, essentially, down the side. And so whether or not you need the salt, whether or not the salt could help destabilize things, there's a lot of discussion about, but that's about where they stand. And then your last question I remember. So here's where we are now. We're on this ridge line, and we're talking about getting across this little valley to where the salt, to where the light layer is exposed right along this edge. So that gives you somewhat of a sense. Let's see, it's taken us 6 years to get to here, though. So yeah, that's why I think if we went as the crow flies, it would just take us a couple of months, but we are really interested in capturing the samples that we've seen and in looking at what's in this valley. So it looks like it's only about 1 kilometer, actually. There is a slope involved, but I guess it's hard to think as the crow flies. I'm used to arguing with 400 people about which direction to go.
We have a question in the overflow room, if it's all right.
Go ahead.
So this might be a little bit
Oh.
but do you think we could extract the water off? And what kind of elements
So a lot of so the mudstones that we see on Mars actually tend to preserve the signature of what we call basaltic rocks or dark volcanic rocks. It's similar to what we see on Earth in Hawaii or Iceland, and it's weathered a little bit. Like there's been water running through it, but in some patches we almost see no evidence for weathering at all. It very much preserves the character of those dark basaltic rocks. So if you're looking at the mudstone, it would have a chemistry very similar to a rock in Hawaii or Iceland, with a little more iron, because all of Mars has a little more iron than Earth. As to whether or not you can extract water or any other kinds of minerals, the water would be pretty hard to extract from these rocks in a way that was useful, but you could get some water out of the atmosphere. And in terms of other minerals, plate tectonics is really key for concentrating metals, for concentrating ores, for concentrating different materials on Earth that we're interested in economically. And so in terms of concentrating like economic minerals, it's very difficult to do that on Mars. A lot of the rocks really look like that primary basaltic kind of composition. In terms of what we might need if we were there and if we had humans there and they wanted to live off the landscape, that is one of the things we look into. As we map out the surface of Mars, we understand a little bit better where there might be different minerals that people would use if they were there. In the 2020 mission that's launching in 2020, that one will have an instrument on board to convert the carbon dioxide atmosphere of Mars into oxygen in kind of a very small amount. But it's just kind of a test thing to keep us moving towards this idea of eventually being able to bring people and to know what they would experience if they were there.
Just take one more over there.
Of the many compounds, of the many compounds studied, is there any evidence signature of oxidation?
Yes. We have a lot of oxidized iron, sulfates. We have oxidized sulfur. The iron is probably the dominant redox mineral. We have hematite.
Does that connote any oxygen?
So it certainly probably happened in reactions with water. So H2O, and you could bind up that oxygen with the iron to make some of the hematite and iron oxides.
All right, one more.
So, so when you dug in there, what have you found?
When we dug with the drill right here?
Yeah.
Yeah. Well, we looked through, and through this whole time, there was a lot of, through all the time represented in all these different rocks, there was a lot of water on Mars. And so that water is saved in a lot of these rocks. And so as we've heated them up, we can see how that lake changed through time and what kind of environment it would have been if anything had lived there. All right, thanks so much.